Alright, now we're going to look at combination circuits. These are circuits that have parts which are parallel and parts that are series. And the way really to start how to solve these different pieces and parts of this is to simplify the circuit down as much as possible. And then we'll work backwards through the circuit from that end. Alright, so to simplify this down, let's look at first. Now this is the original circuit. This is where we're starting. And we're going to figure out how do we get here, which is a little bit more simplified. And how we're doing that is we're going to take this branch of the circuit here and simplify it down. Now if we just look at the portion that's in yellow there, that's a series circuit, which means that total resistance can be found by simply adding the resistors values together. So just on that branch, so we're going to find the resistance of, let's just call that R2, R3, since it's both of those. Well, it's going to equal 380 ohms plus 60 ohms. Alright, so if we put those together, we get a total of 440 ohms. So you can see that's where we get the 440 ohms there. And notice there's only one resistor now on that branch. So we're going to take that guy now and we're going to simplify it down. So now if we look at the next piece over here, it's a little complicated. Okay, these two branches, or these two lines together, those two are parallel because of course it splits right here. So we're splitting the circuit right there. So there's two separate branches, it's parallel, and then of course they come back together at this end. Okay? So if it's parallel, total resistance on that portion of the circuit can be simplified down to this. Now we got to remember our rules for finding resistance. So this would be the resistance of, resistance of R2, R3, and R4 all combined together. It's getting to be a bit much. But we have to say, take the reciprocal of the sums of the reciprocals. Yeah. So the reciprocal of 440 is 1 over 440 ohms. And the sum of those, so that's 1 point. So this one would be 1.1 kiloohms. And when we simplify that down, it comes out 314.29 ohms, which is where we get that number there. All right. And then we can finally reduce that last one down one more time. Now we have a series circuit, so we can finally find the total resistance for the entire circuit by adding those three together, because those three are in series. So that would be 125 ohms plus 314.29 ohms plus 440 ohms, which comes out to a grand total of 879.29 ohms. And that is our total resistance on this circuit. Bloop. Now that we know total resistance, we can find some other things. How fun. So to find the total current, we need to break out our Ohm's law. And in this case, since we're looking for current, if you remember that little triangle there, you're going to cover up the I. And if we cover up the I, which is there, okay, then what we're going to be left with is volts over resistance. Okay, and now we already know the total volts on the battery, or on the circuit, given over here at the battery, is 12 volts. So this is 12 volts. Total resistance we calculated on the last page, and that is 800 and 79.29 ohms. So our total current in amps comes out to be 0.013647 amps. And when we convert that into SI and engineering notation, it comes out, let's see how many spaces we're going to move this guy over. We're going to move it over 1, 2, 3, and that gives us 2 digits in front of the decimal, so we're good. So this becomes 13.647, and we moved it 3 spaces to the right, so this becomes 10 to the negative third, which is milliamps. And that is our total current. Now we can find the voltage drop on each resistor. Now that we know the total current, we can start working backwards to find the current on each one of the resistors and then the voltage drop on each one of those resistors. So if we go back a step here, this is what the circuit looked like before we had it down to the most simplified version. If we look at that, that's a circuit in series. So we know that at each one of those spots, the current will be the same, correct? So each one of these has a current of 13.647 milliamps. Okay. Now knowing that, oh, I missed the 6 in there. Now we can calculate the voltage drop on each one of those circuits. So we're going to use the old Ohm's law. So the volts on resistor 1, voltage drop on resistor 1, would be the current of resistor 1, times the resistance on resistor 1. Alright, so in this case we have the current, which is the same across the circuit because right now we're looking at a series portion of the circuit, times the amperage at that resistor there, resistor 1. Okay, and then if we go ahead and enter this in our calculator, we get voltage drop at resistor 1 equals 1.71 ohms. Nope, volts. Testing you. Now for the voltage drop on resistor 234. Which would be resistor 234's current times the resistance of resistor 234. So voltage, we don't know. Current is the same all around because we're series. So it's 13.647 milliamps. And the ohms, see if I got room. Oh, we're going to squeeze this in there. 314.29 ohms. All right, plug that in the calculator. And that equals 4.29 volts. And for our last resistor, resistor 5, the voltage can be found by doing the current of voltage or resistor 5 times the resistance of resistor 5. So that would equal hold on, okay, so it would equal 13.647 milliamps times 440 ohms equals 6.00 volts. Now a quick check you can kind of do in your head is look at each one of these voltages here. Remember, those have to add up to equal the total volts. And if you do look at them, the total volts is 12, and if I approximate in my head, I can tell that it will come out approximately 12 volts. So we're pretty good there. Let's go ahead and move on. Now we're going to have to break apart that resistor 2, 3, 4 slightly here in the next step. So from what we previously have done, we know some information about this parallel circuit over here. We know that the total voltage on those two resistors you can see, but 3 total, is 4.29 volts. We know that the current for that parallel portion of the circuit is 13.647 milliamps. And we know the total resistance for that, but that's really not as important at the moment. So looking at the voltage, first of all, the voltage drop here, since this is a parallel portion of the circuit, the voltage drop on both those resistors will be the same. However, the current will be different. So what we really need to calculate here, even though we know the voltage on resistor 4 equals 4.29 volts, and we know the voltage on resistor 2, 3 equals 4.29 volts. Now we need to find the current on each one of those. Okay, so we know the voltage drop on each one, just wrote it down. We know the resistance, which is in the diagram. So now we need to solve for current. To solve for current, remember, you could look at that little triangle, cover up the I, and you find out that the current, let's say on resistor 4, equals the voltage of resistor 4 divided by the resistance on resistor 4. Okay, so the current on resistor 4 equals 4.29 volts divided by 1.1 kiloohms, which equals 0.0039 amps. Now, of course, we can't leave it like that. That would be ridiculous. So what we're going to do is we're going to switch that over to our engineering and SI units. So we're going to move that guy over 3 spots. So that would equal, I'm going to squeeze it in here, I don't like this, but it would equal 3.9 milliamps. Alright, so that's our current on resistor 4. That guy's done. I kind of squeezed a lot in here, so I'm going to box this off. And we're going to do the current on resistor 2, 3 next. So same thing here. The current on resistor 2, 3 will equal the volts on resistor 2, 3 divided by the resistance on resistor 2, 3. So it would be 4.29 volts divided by, I got carried away there, divided by, what do we have here? What's the resistance is 440 ohms. All right, that equals 0.0098 amps, which if we change it into our SI units, engineering notation, that would become, let's move that guy over 3. That didn't quite look right, but if I move it there behind the 9, that leaves me 1 digit in front of the decimal. Perfect, that's all I need. So it's 9.8 milliamps. So now we know the current on resistor 2, 3, and we're almost there. One more step. All right, now we're going to look at this last part of the circuit, which is a series portion. We know a couple things already about this. We know the voltage, which is 4.29 volts. We know the current through resistors 2 and 3 combined is 9.8 milliamps. Okay, so using that information, we should be able to figure out, knowing that this is a series circuit, the voltage drop in current through resistors 2 and 3. All right, so If we remember correctly, the voltage will differ between these two, but the current will remain the same. So the current through resistor 2 will be 9.8 milliamps. The current through resistor 3 will be 9.8 milliamps because we're dealing with a series. Okay, the voltage drop will differ though. All right, and we know the resistance, so we need to solve for the voltage drop for both of those combined. Okay, or well, not combined, but separately. So the voltage drop on R2 would equal the current on R2 times the resistance of R2. So looking at what we have here, the current on R2 is 9.8 milliamps. The resistance on R2 is 380 ohms. So those two multiplied together will equal 3.724 volts. We could just say, let's round that back off here. Let's make that 7.2. All right, we're almost there. We're almost to our last voltage drop. All right, so looking at this last one, we want the voltage drop on resistor 3, which will equal the current on resistor 3 times the resistance on resistor 3. So that would be 9.8 milliamps times 60 ohms. And so the voltage on resistor 3 equals 0.588 volts, which is, if I move that back 588 millivolts. So it's in the correct notation. And we are done. We found all the voltage drops on every resistor. We found the current on every resistor. And we know the total voltage, total current, total resistance for the circuit. So that's it. Enjoy.